Okay, good morning, everyone. My name is Mohammed Ibrahim. Today I'm the presenter going to present analysis and design of low power consumption, 8 transistor and 10 transistor full adder CMOS technology. Before we enter, we talk about the today's chip size. So as we know that, the today's chip sizes are reducing and reducing, and the performance of the chips also increasing at the same time. Okay, so first there is a nowadays, so the chip size are reduced to 7 nanometers, but the Apple M1 processors are using the 5 nanometer technology, but the experimental chips are reduced the size to the 2.5 nanometer technology. So at the bottom you can see the some other M1 chips, so the sizes. So you can see that M1, so which has a size of 5 nanometers, so the other one 5.5, and another one is a 6 nanometer technology. Okay, first CMOS. Okay, the term CMOS is stands for complementary metal oxide semiconductor. So this is the most popular technology in the computer chip design industry, and it's broadly used today to form integrated circuits in numerous and varied applications. So the technologies which are made using this technology is computer memories, CPUs, and cell phones. So it uses the P channel and N channel MOSFETs to design the circuits. Next, okay, about my project. So in this project, I have designing high performance and low power consumption CMOS technology using the small number of transistors, full array. Okay, so why we need the low power VLSI chips? So first, it needs, to reduce the power distributions. So means the low device density and then low operating frequency. And now it is important is due to high device density, high operating frequency, and proliferation of portable consumers electronics and concerns on environment and energy resources. Okay, importance of the low power designs. Okay, first it is cost factor for high end systems. So high end systems which needs cooling and packet cost, so it's going to be high, and then air cooled techniques which reaching the limits, and then the electricity city bill will be increased, and then the reliability of the system will be changed. And then okay, desktop PCs consume like around 10 percentage power in US, so means they are using PCs like most of the people's using the PC, so which is consumed like more than 10% in the US. And then usability of portable systems, so which depends on the battery lifetime, and then the restrictions factor for the high performance server design. So the power determines the processor density. So depends on the power, the processor density will be changed. And then so next, so this is the formula which is used for low power designs. So we are considering using this formula, which is P is equal to P switching times P circuit times P leakage plus statics. So the definition, switching power P. So this is a formula, and then the short circuit power. So which are like the explained formulas are here, and then the sigma is the switching activity factor, and then the low power design would look at the trade-offs of the above issues. So we will consider this above issues, and then we will design the design of the chips. And then okay, these are the basic full adder formula, circuit diagram, and then the truth table. So this is the formula, which is A X NOR B, and then X NOR C in, and then the for the C out, finding the C out. So A dot B plus A X NOR B. Okay, so this is the basic the below picture which shows the basic circuit diagram of the full adder, and then the right side it shows the full adder truth table. This is basic full adder truth table. Depends on this, we are going to validate our system circuit diagram. Okay, second, methodology. Okay, first we are going to use the two different softwares, which is first one is DSCH, which is digital schematic diagram, which is used for designing the circuit, and then the microwave, which is used to generate the layout, and then find the power consumption, speed of the processor, and then at the same time the time delay. Okay, so on the right side, we can see the step of processes. So how we are going to do the simulation. First, we are starting with opening the selecting technology, which it can be like 65 nanometer or 90 nanometer from the foundry, and then creating 8 transistor and 10 transistor full adder design, and then we are saving it, and then we are running the simulation. So if there is there's no error in the circuit, then we are generating the spice file and then Verilog file. So the Verilog file it's going to be simulated in the microwave tool to get the layout for that circuit diagram, and then when and then we are running the simulation, and then we get the results. Okay, next. So this is the design architecture of 10 transistor and 8 transistor full adder circuit diagram. So on the left hand side, we can see the 10 transistor full adder circuit diagram. On the right side, we can see the 8 transistor full adder circuit diagram. So this is the layout for the circuit diagram, and it has like input 1, input 2, output 1, input 3, and then output 2. So total 3 inputs and then 2 outputs. Next, 80 full adder transistor layout, so which is has same like 3 inputs and then 2 outputs. So this is the layout for the 8 transistor. And then next, result and conclusions. Okay, so first for the 10 transistor full adder simulation result. So the figure below, which shows the waveform of the output for the 10 transistor circuit diagram, and then the blue line shows the blue lines here. It shows the number 0, and then the red line shows which is the input going to higher, which is 1, and then these values are validated with the basic full adder truth table, and then if it's valid correctly, and then we are considering which is running. I mean, it has like correct outputs at the same time. And this is our output from the microbin tool, which is using the layout. So it shows the input and then input 3 inputs and then 2 outputs. So in the second output, we are getting the time delay, which is 8 nanoseconds, and then the speed of the circuit diagram, which is 0.13 gigahertz. And then for the 8 transistor, so this is the waveform, which is get from the DSCH2 from the circuit diagram. And then so it also show, I mean, validate with using the basic full adder truth table. And then so this is the result for from the simulation of microwave tool. So which shows the 80 transistor, which has like time delay of 0.880, and then the speed is 1.15 gigahertz. And so this is the simulation result. So which is on the right hand side. So we can see the table, which has like proposed 2 adder, I mean proposed adders, and then transistor power in microwatts, time in nanoseconds, speed in gigahertz, and then the power delay product. So okay, first for the 10 transistor, so we're getting the power, which is 3 microwatts, and then for the 8 transistor, we are getting 71 microwatts. And then for the time delay, we are getting for the 10 transistor, which is 8 nanoseconds. For the 10 transistor, we are getting the 8 nanoseconds. For the 8 transistor, we are getting 0.880 nanoseconds. And then for the speed, we are having like 0.13 gigahertz for 10 transistor, and then for the 8 transistor, we are getting 1.1550. For the power delay product, so we are multiplying the power and the time delay. So we are getting 28.896, and then for the 8 transistor, we are getting 63.132. Okay. So these are like recorded from the microwave tool simulation. And then in the discussion, the power distribution depends on the chip temperature and its size. Okay, whenever the temperature of the chip increases, it consumes like more power than we expected. And at the same time, if the chip has like higher performance, the same power problem can be became fine in there. So when the higher performance, the temperature also increases, depends on the chip size and the density. Okay, Okay, in the summary, so the proposed design 80 has the higher speed and then less time delay than the proposed 20, which is made of a combination of CMOS, because we saw that the 80 has like very less time delay at the same time. So we are considering this technology is used as the basis for design that are proposed for low power and then high performance approximation ideas. So we are taking this 8 transistor design is suitable for VLSI designs. Thank you, everyone.